Hello, today we will be talking about denoising and compressing data with a matrix decomposition technique called singular value decomposition, which has connections both to eigendecomposition as well as to principal components analysis. Recall that dimensionality reduction is a key motivation for representation learning techniques like PCA. Of course, reducing the number of dimensions is useful for visualization because you can only visualize one or two dimensions. But it's also useful for compressing data and storing a simpler form of the data, as well as denoising data, which amounts to taking away some components of the data that we think are artifactual and not part of the real signal. Recall that when we looked at the Wines data set, we looked at a scree plot that showed us how much variance was explained by each principal component. And we saw that there were only about 3 significant components. This is actually generally true of most data sets, that there's a lot fewer significant components than the number of features. This suggests that we can recreate the data using fewer features. But in order to do this, we have to understand a decomposition technique called singular value decomposition. You can think of singular value decomposition as a generalization of eigendecomposition to non-square matrices. If you had a square matrix, singular value decomposition, once again, is a decomposition into a rotation times a scaling times another rotation. But it generalizes to non-square cases, which means we can directly apply it on our data. A couple of more details about this type of decomposition. Similar to eigendecomposition, U and V are orthogonal matrices, and they have orthonormal column vectors. This means that U times U transpose, or V times V transpose, is equal to the identity. Here is actually the connection between SVD and eigendecomposition. Suppose you have a matrix A and you can singular value decompose it as U, S, V transpose. Look what happens when we multiply A by A transpose. We get a V times V transpose here that drops out to an identity. So you have U, S squared times U transpose. But U transpose is also equal to its inverse. So we get an expression that looks remarkably like an eigendecomposition. And in fact, it is. In fact, the left singular vectors of A are eigenvectors of AA transpose. And the right singular vectors are eigenvectors of A transpose A. And the eigenvalues are the squares of the singular values. We can in fact also use SVD to directly compute PCA. Suppose our data matrix X has SVD US V transpose. Recall that PCA was defined as the eigendecomposition of the covariance matrix. But in the cases where the covariance matrix is mean-centered, this reduces to finding eigenvectors of XX transpose. Here, by convention, we had our rows and columns flipped, but these are actually the eigenvectors of the matrix X transpose X in the original way we'd oriented our data. And therefore, the eigenvectors of our covariance matrix are found in the columns of V. So they're just found in our singular value decomposition. Not only are the eigenvectors or principal axes just found there, we can actually just find the principal components there too. How can we do that? The principal components are X times V. But if you use this equation and substitute it, you get U times S and V transpose times V. This drops out to an identity. And therefore, the principal components are just U times S. So in one fell swoop, you got both the principal components and principal axes when you use SVD to compute PCA. And often, this is actually the preferred method for computing PCA. SVD can not only be used to compute PCA, but can also be used to low-rank approximate the data. That means approximate the data with fewer components than what you were given. So suppose we have a data matrix that's M by N. You can have a singular value decomposition to U, sigma, V transpose. But you can chop off some singular vectors and some singular values and recreate the same matrix without some of the signals. So let's see an example of doing this. Suppose we chopped off this column, this row, and this column, and this row. What do we get then? We get m times some other dimension r, but here we've chopped off an equivalent number of rows and columns. So we have r times r, and here we have r times n, because we didn't do anything with the column count. This once again equals m times n, so we have the same matrix dimensions. So we've recreated the data without these singular vectors and values. So one advantage of this is you can store fewer components per data point and still be confident that you can recreate the data matrix to some degree of accuracy. And this is actually shown here on an image data set. So the original image data set has images with a lot of features. This has 1070 by 942 pixels. So the number of features is this value here times this value. But suppose we don't want to store so many features. Can we get away with storing fewer? This is the reconstruction of this image using only 80 features. Still looks remarkably like Einstein. And in fact, the degradation is very slow. If I only used 40, I only get a slightly blurrier image. And even with 10, you can pretty much tell who this person is. And this is why you can low-rank approximate a lot of data sets, because you can actually reconstruct them with a lot fewer components. And the final application I'll talk about for low-rank approximation today is denoising the data. Usually, when we have noise in the data, it can be anywhere. It can be all over our data features. Here, I've added what's called salt and pepper noise, which substitutes 1 for about a quarter of the pixels and 0 for about a quarter of the pixels here. But when you do singular value decomposition, you have reordered the features so that they can go from the ones that explain the most variance to the least variance. So when you chop off the ones that don't explain very much variation, you're usually chopping off noise. And you see that's exactly what happens. The salt and pepperiness of the data goes away. You do get a blurrier picture. You've also denoised the data set. And this is another application of SVD and in turn PCA.